Here's the introduction portion of our presentation. Moving forward, we have the study goals. Our main goal is to investigate the difference between charter schools and public schools in New York City. The main metric would be standardized test scores, specifically the percentage of students in advanced and proficient categories for both math and English. Therefore, our H0 would be coefficient of regression model 0 and HA, coefficient of regression model non-zero. Hopefully this will allow us to see if charter schools are a worthwhile monetary investment. Along with this test, we want to see if there are any other significant factors that could help us evaluate school performance. Our previous studies were charter school performance in New Jersey from Jason Barr, Department of Economics, and evaluating the performance of Philadelphia's charter schools, Ron Zimmer, Suzanne Blank. Moving on to performance of charter schools in Wisconsin, John White, David Weimer, and others. We will focus on the performance of Philadelphia's charter school study in the next slide. Continuing, we have evaluating the performance of Philadelphia's charter schools. From their analysis, among the other analysis of the Philadelphia paper examines the relationship between grade level and improvements. We see a table here with variables of attending in charter schools during the first 3 years of their operation and then at least 4 years moving forward, as well as their high school students and their K through 8 students. We see their robust standard errors for math and the reading. And the asterisks are indicated significant significance at the 5% level. Moving forward, the author warns that they did not have any information on the dropout rates for the high schools, which could bias the results further in either direction. They did have information on K through 8 students switching out of charter schools, and including that information caused the results to regress closer towards the mean of 0. They modeled success across numerous different standardized tests. To do this, they took each student's score and converted it to a z-score with a mean of 0 and standard deviation of 1. In the process, they assumed that the distribution of scores is independent of charter status, which could be argued. We obtained the data from the Pennsylvania school system. They publicize all the data that they collect on their schools, and the following site below indicates the 5 categories of the data sets: finance, people, outcomes, social or school characteristics, and comprehensive. Each of these are split on the state, district, and school level.
All right, my name is Alan. I'm going to give you an introduction to dataset characteristics. We're talking about 1,613 variables on 34,610 rows on the Pennsylvania school system dataset. This gives us 11 years of data over 3,000 Pennsylvania schools. We're going to take preliminary selection in each of our datasets, the outcomes, the people, and the school characteristics / opportunities. The outcome section, we're going to cover most of the information that we need for response variables. After cutting down from 818 variables to 41 variables, we have these 41 variables, and we're going to use variables 22 to 41 for our response variables, 1 to 12 to merge the data frames back together. The people dataset will tell us about the demographics, about the social and financial backgrounds. These are the dataset we're going to use for social, for the people dataset. And the preliminary opportunities dataset will tell us a lot about what the school offers, specifically what the classes are, what kind of classes the school offers. We will merge our dataset back together and we'll retain all the rows with 61 variables, and we'll move through section by section analyzing the data that we have collected. These are the basic observations through the specific variables. For example, as you can see, the attendance rate, the minimum has 38.68%. We'll see that most of the demographic information is okay. We are a little bit suspicious about the zeros. It may be actual 0 or it may be a missing value. So if there are too many missing values, we'll remove it. Math is mostly presented, and the ELA, English language acquisition, is missing in most of the cases. After trimming all the missing variables, we are left with 44 variables, and these variables are all self-explanatory by the name. The name is very clear. Our open data variable is the number of days after January 1st, 1900. Free and reduced lunch eligible students and number of limited English students are also raw counts of the students. So these are numeric data we will use. They are all 0 to 100 percentage wise. And we're going to focus on the advanced proficient groups combined. Therefore, the basic and below basic values will eventually go unused. So as a conclusion, we are left with 38 variables, and we have 3,428 unique schools on 34,610 observations. So we from the years 2006 to 2016, and we will dig deeper to how we clean our data.
Our overall goal in this study is to gauge the success of different schools in our Pennsylvania dataset. Since there's no explicit variable that labels the success of a school, we'll have to make our own. For math, it's simple. We take the percentage of students in the proficient group and advanced groups based on the standardized test. For the English, we have to take a mixture of English language ability and reading and writing. From the years 2006 to 2014, schools used a combination of reading and writing, and from 2014 to 2017, they combined both into an ELA metric. So we will have to use that for those years.
Since one of our main question is the difference between charter school and district schools, we can test indicators to compare the two across the years. As we can clearly see from the line plots, the change in standardized test in 2014 affected the math score as well, lowering the average scores. This result could show that the charter school typically underperform relative to their district school counterparts. From these two graphs, we can see that both of our indicators are approximately normally distributed, which is a good sign for further analysis. If we run into problems in the futures, we may attempt to transform our data to fix a slight left skew. Actually, we have some concerns. Our biggest concern with our analysis is the difference between charter school and district schools and any interactive effects. Our preliminary analysis will assume that the interactive effects are minor, but if necessary, we may have to make two separate models. We want to make sure that the distribution of our other explanatory values are independent of the status of our schools. One preconception about charter school is they are generally smaller in size than district schools. However, we have that the median of district schools is 495 and charter school have a medium size of 487. So we can see these two mediums are kind of close. And we see from those histograms that they are similarly distributed. So we can assume that the school size and charter school status are independent. Another preconception is that the charter school has a smaller student-teacher ratios. However, we look at the medians. The medians of district schools is 14.72, while the charter school has a median size of 15.19. So we can see the two medians are pretty close, and we can see from those histograms that they are similarly distributed. So we can assume that the student-teacher ratios and charter school status are independent. We also considered about the demographic distributions. Unfortunately, the demographic distributions between charter school and district schools is not at all similar. So basically we can see from these two pie charts, we can see that the charter school have a much larger minority population than district schools. So if the demographic information plays a large part in our preliminary regressions, we may need to consider creating two separate models.
We see that we have a lot of different variables talking about the demographic distribution of our schools. First, we want to divide out by the total school size so that these become percentages and are not dependent on the school size. Next, we see that if we add up all of our demographic information, they will frequently sum to 1 as seen by the histogram on the top. That means that we do not want to use all of them because we will get a interdependence, and summing up all of them will give us the final variable. We see that since we have to remove one, we will remove the percentage of the school that is a white population, since that is frequently the largest variable as seen in the histogram on the bottom.
For first regressions, we use the following explanatory variables in their adjusted status: academic years, open date, total enrollment, demographic informations, low income percentage, limited English percentage, pupil-teacher ratios, and the result will be shown on the next slide. This is the result for regression math, which is showing the relationship with the explanatory variables we talked about in the previous slide. This is the regression ELA, the result from the R program. Based on the result from the R program we shown in the previous two slides, we can see that in both cases it appears that our residuals are not normal and may need additional transformations. So we will evaluate our residuals further in the next part as we analyze and improve our models.
Hello, this is Jun Kim, and I will talk about the photo analysis. First, we want to check for outliers. Using the ESD method, we check for outlier in our response variable, and from the all output below, you could see there was multiple outliers, so we removed them from our data. Next, we will check for outlier in our explanatory variables. From the graph, you could see several outliers, but we will remove the 5 most extreme values since they have a clear distinction and move on. Here we could see a before and after of our leverage plot, and after removing the outlier, you could clearly see our residuals have become more linear. Next, we want to check for normality of residual. In the following slide, you will see some odd behavior at the edges of the QQ plot. This is due to our response variable being a percentage and must be between 0 and 100. Unfortunately, due to all limitation, we cannot use the Shapiro test in R. Luckily, from viewing the histogram, our residual appear approximately normal. And here is the slides. And you can see at the bottom two graphs, you could see some real behavior at the end of the QQ plot, and the histogram on top for both of the response variable look relatively normal. Next, we want to check for constant variance in our data. In the following slide, you will see the scale location plot, and you're going to see quite a few problems. So we will attempt to fix our non-constant variance with the Box-Cox procedure. And these are our slides. And in the bottom two slide, you could clearly see the line is not linear. So after using the Box-Cox transformation, which takes our response variable to some power lambda, we could see our lambda value is close to 1.5, and you will see the effects of the transformation on the next slide. And you could see, although it's not perfect, it is much better than before. Next, we want to check for multicollinearity. After calculating the VIF for all the variables, it seemed that none of the VIF is greater than 10, so it seemed none of the variables indicate excessive multicollinearity. However, the black and low income percentage variable seemed to have some correlation in the graph, but after calculating the R-square, we concluded this is not a problem in our model. Now on to further concerns. As of right now, we still have a lot of statistically significant variables than we would like, so we tried to perform a best subset analysis. Unfortunately, due to the large amount of data, R cannot process all of this. Even taking 10% of the data is still too large. And since the distribution differ between charter school and district school, we will present two different models in our conclusion. And here is the final models. You could see many of the variables are significant, but we will put more detail in the next slide.
Hello, this is Dan, and I'll be discussing the conclusion of our project and summarizing our findings. So here is our math model, which is free from outliers and other types of violations. Comparing this to our preliminary model, we see that the Hispanic explanatory variable is no longer significant, and the rest of the variables remain statistically significant. Here is our final English language arts model, where the Hispanic variable went from insignificant to significant after the revisions, and pupil-teacher ratio remains insignificant. So for revisions made, our preliminary model only considered the first order terms, used all the observations available, had several serious outliers, and had a non-constant variance. In order to remedy this, the outliers were removed using the critical points according to the studentized residuals as well as hat values. The non-constant variance was corrected through the Box-Cox procedure, where the procedure gave us a lambda value of 1.5. To confirm our assumption, we checked for any collinearity and we found none. And after all these modifications, all of our assumptions were met for valid regression. So our primary research question was to assess the difference between charter schools and district schools. If you were to take a sample mean of the indicator between the two, we would see that charter schools perform relatively worse to district schools. We see that in our model, we take into consideration all the other factors giving a different result. Both of our models had school districts as a statistically significant factor. The effect was opposite between the English language arts and math. And both had an effect size of less than 30 under our transformation of 1.15 and our standard deviation of our response variable. Our model would suggest that charter schools have a higher level of performance in English-related classes, while district schools have an advantage in mathematics.
Beyond our primary research question of looking for a statistical difference between charter schools and district schools, we also wanted to look for impactful factors overall to a school's performance. According to our model, a school age was a significant factor. A school that was 10 years older is correlated to an increase in 1/10 of a standard deviation of our response variable. This roughly corresponds to a 2% increase in students in the proficient and advanced groups for both testing categories. It also seems that a smaller school size corresponds to a better performance. This is not reflected in the pupil-teacher ratio like one would assume. So it doesn't matter that there's less students in the classroom, just that there's less students in the school. Of all the demographic information that we used, Native American percentages seem to have the most impact. An increase in 5% of the population of Native American students roughly corresponded to 1/3 of a standard deviation increase. We should note that the number of schools with large Native American populations was fairly limited, so we should probably be careful using it as a strong predictor. One of the studies listed in the first part of this presentation also used a regression analysis and hypothesized that while there may not be a statistical difference between charter schools and district schools overall, there may be a statistical difference for a certain subset of students. In our entire data set of variables, all 118 of them, there was one specific variable that isolates the performance of historically underperforming students. If we use this as a predictor, in our simple model, we see that the factor coefficient for charter schools switches to positive, implying that there is a statistically significant difference, and these students will benefit from charter schools more than the student population as a whole. In Pennsylvania, these historically underperforming students are defined as students with disabilities or economically disadvantaged students and English language learners. Our overall conclusion for this is that while charter schools underperform related to public schools on average, they serve different populations, and for some people, charter schools are the better choice still. Charter schools, for example, may be better at teaching historically underperforming students than district schools are. And the effect of certain factors remain constant between charter and public schools, such as age and total enrollment.
So for some considerations for further studies, one of the pieces of information that was that this dataset did not have was geographical information. There's no guarantee that charter schools and district schools are equally distributed throughout the state. It could be possible that district schools are placed in locations where resources are better, and we cannot detect that within our regression. Pennsylvania stopped recording the performance of traditionally underperforming students, as well as the breakdown of students' performance by racial demographics in 2014 and 2010, respectively. If possible, without violating any privacy of these individuals, it would be a useful avenue for further research.